All right, so now welcome back for real. It's a different video now, and I'm going to start problem number 38. So it says a 5 kilogram object is initially at rest at the origin. So it's at rest, meaning the initial velocity is 0, and it's at the origin, the initial position is also 0. It is subjected to the time varying force shown in the figure. So the force is shown to us. What is the object's velocity at time t equal to 6 seconds? So we have an object and it's being pulled by a time varying force. So the force here starts being 0, and then the force increases linearly from 0 newtons to 5 to 10 newtons. So it increases linearly, and then the force drops again and becomes 0. So when there is force, when there is a net force, there is an acceleration. When the force drops to 0, the acceleration will be 0. So that means the velocity will increase in this interval, but then at this interval of time, the velocity will remain constant because the net force is 0, therefore the acceleration will be 0, and therefore the velocity will be constant. So what is the velocity that you get by going from here to here? Well, let's first calculate the acceleration. The acceleration is the force over mass, because the force is ma, so we know that F equals to ma, and so the acceleration would just be the force over the mass. And since the mass is 5 kilograms, so it would be the force divided by 5 kilograms. So whatever the force is here, so when the force is 0, you divide by 0. So you divide this graph by 5 kilograms. So if you like, I would just do it, I would divide by 5 kilograms here, so it would be 1 meter per second squared when the force is 5 newtons. And when the force is 10 newtons, it would be 2 meters per second squared all the way to here. So let me just draw it this way. That's the acceleration. And then here, the acceleration would become 0 again. I mean, if you want, you can find the equation of the line. No reason to do that. Or actually, yeah, why not? Let me find the equation of this line, of this line, and then find the acceleration. So during the time between 2 and 4 seconds, the force will be what? Well, on the y-axis you have the force, on the x-axis you have the time. So the force will just be the slope times the x-axis, because the y-intercept is 0. The slope is what? Rise over run, so 10 over 4, or 5 over 2, 2.5. So 2.5, so 2.5 times t, 2.5 times t. Let's verify that. When t is 0, you get 0. When t is 2, when t is 2, the force is 5. And when t is 4, you get 10. Yeah, so that's the formula for the force. So the acceleration will be the force over the mass. The mass is 5, so divide this by 5, you get 0.5. So 0.5 times t. Which makes sense. When t is 0, the acceleration is 0. When t is 2 seconds, the acceleration is 1 meter per second squared. And when t is 4 seconds, the acceleration is 2. Yeah, sounds good. So what's the velocity? The velocity is the antiderivative of the acceleration. I'll do it the hard way, and then I just tell you the easy way. So the velocity is the antiderivative of acceleration. So it would be, the velocity would just be the integral of acceleration. What's the integral of this? It would be 0.25 t squared, right? So this becomes a 2, and you have to divide by a 2, and then plus some constant, because it's just the antiderivative. And we can determine what that constant is. That constant is 0, because the velocity at t equal to 0, it was at rest. It's at rest at the origin. So when you substitute t equal to 0, I need 0 on the left side. So this is 0. Left side is 0. So c itself is 0. So I would just erase the c. So that's the velocity as a function of time. That's the velocity as a function of time. And so what's the velocity at t equal to 4 seconds? At t equal to 4 seconds, well, you substitute 4 seconds. So the velocity at t equal to 4 seconds, you substitute 4 here. So when you substitute 4, you get 4. 4 squared is 16. And 16 times 0.25 is 4. So you get 4 meters per second. So that's the velocity at t equal to 4 seconds. It's at t equal to 4 seconds. Yeah, the velocity is 4 meters per second squared, and then they said, what's the velocity at t equal to 6 seconds? Well, at 6 seconds, at 4 seconds, the velocity would be 4 meters per second, but between 4 and 6, there is no acceleration, so the velocity will remain constant. So it will remain being 4 meters per second squared. A different way to do it, since the velocity is the integral of acceleration, what you can do is simply say, well, it's the area under the curve. So it's this area. It's this area. What's that area? Well, for a triangle, it's half the base times the height. Half the base, half of 4 is 2, times the height is 2. The height is 2, and so that's 4. So you get 4. So you can do it that way. And if I ask you what's the position at t equal to 4 seconds, what's the position at t equal to 4 seconds? Well, the position is the integral of velocity. So you integrate this. The position will just be the integral. So when you integrate this, you get, by the way, let me write 0.25 as a fourth, as 1/4. So when you integrate this, right, 1 over 4 is 0.25. So when you integrate this, this becomes t cubed, but you have to divide by 3. So when you divide by 3, but you still have a fourth here, so this becomes 1/12. 1/12 plus a constant, right? It's the integral plus a constant. But I know that the position was 0. It was at the origin at t equal to 0. So when you substitute t equal to 0, you get 0 on the left side. So that constant is also 0. So we erase it. So it's just that. That's the position versus time. And so what's the position at t equal to 4 seconds? So the position at t equal to 4 seconds will be, well, you substitute 4 seconds here. So 4 times 4 times 4 cubed, that's 64, and you get 64 over 12. It's 64 over 12. Well, 64 over 4 is 16, so 16 over 3, and that's 5.333. So that's about 5.3 meters. So at t equal to 4 seconds, the position is 5.3 meters. What's the position at t equal to 6 seconds, if I ask you? Well, you have to first find the position, your position at t equal to 4 seconds. It's 5.3. And then ask what happens at t equal to 4 seconds, between 4 and 6 seconds. 4 and 6 seconds, this formula for position only applies between 0 and 4 seconds, because that's when the acceleration has this form. After that, the acceleration is 0, and the velocity is simply 4. So between 4 and 6 seconds, you're moving at 4 meters per second. So 4 to 6 seconds, that's 2 additional seconds. So 2 additional seconds times 4, that's 8 additional meters. So the position at 6 seconds will equal to the position at 4 seconds, which is 5.3, plus the velocity times the additional time, which is 2 more seconds. So that's in 2 seconds you have moved it by 8, so that's 13.3 meters. That's your position at that. Okay. All right. But they didn't ask this question. I just made it up. All right. So let us continue. We go to this next problem here, and I will read it. It says, a baggage handler drops your 10-kilogram suitcase onto a conveyor belt running at 2 meters per second. So the conveyor belt is running, and then the person drops your luggage, your 10-kilogram suitcase, and then it says the materials are such that mu s, the coefficient of static friction between the bag and the conveyor belt, is 0.5, and the coefficient of kinetic friction is 0.3. And then it says, how far is your suitcase dragged before it is riding smoothly on the belt? Okay. So what happens is, let's draw something. So here's the belt. The conveyor belt looks something like this. It's just, that's not. So it's moving at a certain speed. It's moving at a certain speed. This is your bag. It just dropped at rest. So when you drop your bag, what's the horizontal velocity of the bag? the x, it does not have any, so you just drop it. It's only moving in the vertical direction. So by the time it drops, it will hit here. It will hit there, and it hits here. The bag has 0 speed. The conveyor belt is moving at 2 meters per second. So here's the conveyor belt moving. The conveyor belt is moving your bag, and your bag is doing this. Eventually, so it will be rubbing against it. So there will be force of kinetic friction between them until your bag catches up in speed and moves at 2 meters per second. So it will be moving at the same speed as the conveyor belt. So it will be moving at the same speed as the conveyor belt. In that case, the bag is moving at 2, the conveyor belt is moving at 2, and so there is no relative motion between them, meaning they don't rub, and so that means the force between them will be just force of static friction, if any. Okay? So who is going to accelerate the bag and make it move with the conveyor belt at that same speed? So the bag has to accelerate from 0 to 2 meters per second squared. So who's going to do that job and make it accelerate? Well, it's the conveyor belt. It's the force of friction between the conveyor belt and the bag. What kind of friction? Well, there will be a relative motion between the two surfaces, and so that force of friction will be force of kinetic friction. So let's calculate the force of kinetic friction. So the bag drops, it will be here, and it will have kinetic friction. So the conveyor belt will be moving still at 2 meters per second squared, and your bag starts moving at 0, and then maybe at 1 meter per second, like 0.5 meters per second squared. The conveyor belt is still faster, so it's still friction. And then your bag goes to 1 meter per second squared. The conveyor belt is still moving at 2, so it's still moving faster. There is still relative motion between the two surfaces. Your bag starts to move at maybe 1.5, and then finally at 2 meters per second, and then they would have the same speed, and then there is no relative motion between them, and then it would just move. Okay, so I know that. Here's your bag. What are the forces on it? There will be a normal force this way, normal force. There will be an mg, and that's it. I'm sorry. And then there will be force of friction. So in what direction will the force of friction be? Well, the bag wants to move this way, wants to just sit there, and the conveyor belt is moving this way. So the relative motion between them will be like that. So to resist the relative motion, the force of friction has to be this way. The force of kinetic friction is that way. And the reason for that, I think it's intuitively also, because eventually your bag has to accelerate and move this way, so the force has to be that way. That's the force of friction. And I know that the force of kinetic friction will equal to the coefficient of kinetic friction times the normal force. And since there is no motion in the y direction, all the action is along the x direction, then the normal force will equal to mg. They have to cancel because there is no motion up and down. So the normal force will equal to mg. So this is mu k times the mass times gravity. Is there another force on the bag along the x direction? The answer is no. There is only friction. That's it. With Newton's laws, if there is no contact between two objects, there is no force between them. There is a normal force because there is contact between the bag and the conveyor belt. There is a force of gravity. That's the only exception because the earth can reach in and grab you and pull you down. That doesn't require contact. There is force of friction because there is contact between the belt and the luggage. And that's it. There are no ropes, there are no strings, there is nobody pushing it. You might say, well, the person who threw it, that person, once it left their hand is no longer there, and it's just gravity, the normal force, and k. So the net force in the x direction will equal to the mass times acceleration. The net force in the x direction is just mu k mg. That's the net force, mu k mg. That's the force on the bag horizontally, and the net force on the bag will equal to the mass of the bag times the acceleration of the bag. And so the mass of the bag goes away, it cancels on both sides. So the acceleration of the bag will just be mu k times gravity, and mu k is 0.3 times 9.8 and I want to use my calculator to do that. .3 times 9.8, and I get 2.94 4 meters per second squared. That's the acceleration. We haven't answered the question yet. They say, how far is your suitcase dragged before it is riding smoothly? So how long will it take? Or how far will the suitcase move before it reaches up to the velocity of the belt? It went from 0 to 2. So I want to reach 2. Well, this is motion at constant acceleration, so I could use my kinematics, where it says v squared minus v initial, you can call it v final squared minus v initial squared is equal to 2 times the acceleration times x final minus x initial. The ending point minus the initial point is the distance that you have to move. The bag moves before it reaches that speed. And so we can call it d. So d will equal to the final speed squared minus the initial speed squared divided by twice the acceleration. And the final speed is 2, so 2 squared. The initial speed was 0 because it was dropped. And it was just dropped this way. It didn't have any velocity that way, I'm assuming. I mean, although the person could throw the bag that way. But I think they should just say dropped. Yeah, it says dropped, so dropped means this way. Divided by twice the acceleration. What's the acceleration? 2.94. And so we get what? Times 2. I get 0.68. 0.68 meters before it comes to rest. Let me just double check my numbers. Yes, that is correct. 0.68. Okay. And that is it. We will, as you notice, the problems in one dimension are not the most interesting, but I promise we will do more interesting problems where you do motion in 2 dimensions. So I would like to do one more problem that has some calculus, just to, we don't forget our calc skills because they will be more and more important this semester. And next semester they are even more important. And then in your 3rd semester of this course, they're even more important. And so we want to get them sharpened. I want 2 things I want you to get, 3 things from this class. I want you to get Newton's laws down really, really well. And then the second thing would be your calculus skills would be very good. And then your vector algebra or vector calculus skills also are needed. They are really critical in semester 2 of physics, electricity and magnetism. You have to know vectors in that class. Okay. Semester 3, not so much, not that many vectors. But semester 2, very critical. So, let me get my blue and green pen here. So it says a time t equal to 0, an object of mass m, so the mass is given, it's m, think of it as a number of kilograms. It's at rest, the object is at rest. What does it mean? Okay, the initial velocity is 0. And the position initially is at x equal to 0. And it's sitting on a horizontal frictionless surface. So the only forces on this object are gravity, and there is the normal force. And they're just equal to each other because the object is not moving up or down. Okay. So that's initially. What happens? Well, starting at t equal to 0, a horizontal force Fx equal to this thing, then you start applying a force, Fx, to it. And so when you apply a force, it will accelerate in the x direction. And the question is, graph, what's the object's velocity, and then graph it. And then what is the object's velocity after a very long time. So initially, when you apply the force, at t equal to 0, the force is just F0, because e to the 0 is 0. Here, e to the minus t over capital T. Capital T is some constant. T is the variable here. And then as t goes to infinity, when the time goes on, you see that the e to the negative infinity will be 0. This thing will become 0. So after a long time, the force will just become 0. And so if the net force is 0, after a long time, the velocity will just be constant. So the velocity initially will increase and increase and increase, but it will increase at a slower and slower rate and eventually reaches some constant velocity. The question is, what is that constant velocity? Well, we know that the net force, by Newton's second law, the net force, let me write it one more time, the net force in the x direction will equal to the mass times the acceleration in the x direction. The net force in the x direction, we're told that's it. This is the force. There is no friction, there is nothing else. So it's only F initial, e to the minus t over capital T, and that's equal to the mass times the acceleration in the x direction. And so we can get the acceleration itself. So the acceleration will just be the force over the mass. So it's F initial over m, those are constants, and then e to the minus t over capital T. That's the acceleration. So what's the velocity? The velocity will be the antiderivative of this. So the velocity will just be, let's integrate this. If you integrate this, you will get, this is a constant, and so you get F initial over m. And when you integrate, remember when you take the derivative of e to the something, it will, a negative 1 over t comes down, so we will anticipate that and we just multiply by t. So it becomes e to the minus t over capital T. If you're not sure about this, if you can't see this step, what you do is take the derivative of this, take the derivative. Derivative of e to the something is e to the something. And then the chain rule says you have to take the derivative of the inside function here. And so that's derivative of negative t over capital T. The t goes away and you just have negative 1 over t comes down. And when you multiply by negative t by negative 1 over t, they cancel and you just have what you had originally, the acceleration. So this checks out. But when you take an antiderivative, there is always some arbitrary constant. Okay, some arbitrary constant. So now, how do I determine that arbitrary constant? I'm told that the velocity is 0 at time t equal to 0. So I'm told that v initial, let's plug in 0 here, v at time t equal to 0 would be F initial over the mass, and then times negative capital T, and then e to the 0 is 1, so that goes away, plus a constant, and so this whole thing will just be 0 because v initial is 0. And therefore this constant c will just equal to capital T F initial over m. That's that. So now go back, whatever you see as c, replace it. So you get v as a function of time will be, let me put the negative t here, negative t f0 over m e to the minus t over capital T plus c, and c is t times f0 over m, like so. And I'm going to factor this t f0 over m. So I get, let me do it here. V will equal to t f0 over m. I'm going to factor it and then do this. When you take this out, you just have a 1 left. And then when you take this out, you just have the negative sign, and then e to the minus capital T over, a little t over capital T. So that's graphic. Here's v. At t equal to 0, well, e to the 0 is 0, and then 1 minus, e to the 0 is 1, and then 1 minus 0, 1 minus 1 is 0. So the velocity is 0 at t equal to 0. And this, if you take the derivative, it's increasing, it's positive, because the acceleration is positive, but it's concave down. If you take the second derivative, you find it's concave down. So it's a positive derivative, but concave down, so it looks like this. It looks like that. And then as t goes to infinity, when t approaches, when you take the limit as t goes to infinity, limit as t goes to infinity of v of t, take that limit. this is constant, and as t goes to infinity of this, you will get e to the minus infinity, which is 0, so that approaches 0, and so this one vanishes. You just have a 1 inside here, so you just get capital T f0 over m. So that's the value you would approach. You would approach it would be like a horizontal asymptote, and that value of that horizontal asymptote is T f0 over m. And I think we have answered all the questions now, because it says, find and graph the object's velocity as a function of time. We graphed it, and we found it. Here it is. That's the velocity as a function of time. And then it says, what is the object's velocity after a very long time? After a very long time, the object's velocity would be that constant value, T f0 over m. That's the object's velocity after a very long time. And let me draw my m really well. If I ask you, what's the object's position after a very long time? That would be infinite, because the object is moving at some speed. That speed starts at 0, but then as the speed increases, the position would go farther and farther. And that speed is not going back to 0. It's just continuing to be constant as t goes to infinity, so the position will be infinite. And you can find it by taking the integral of this, taking the antiderivative of this, and you will find what the position is, and it would be going to infinity as time goes to infinity. Because when you integrate, this one here gives you a time t, and this one will give you like a negative. It will just be the exponential function, pretty much, with a factor of t, capital T. And as t goes to infinity, that part goes to 0, but you will have a t here, and that goes to infinity. Okay, and so that's it for this. Next time we will start chapter 7, 5 and 6. Yeah, we'll start chapter 7, Newton's third law. All right, I'll see you in the next video, next time.